Hello, everybody. Good to see you. I'm so happy to see uh, more than friends. I just came back from a Zoom meeting. There was only a single person on Zoom. I was so happy. I told the guy, "Thank you for coming to hear my talk." He told me, "Professor Bra, I'm the next speaker." Well, good to see you. Good to see you. So I'm going to talk about again measuring, modeling contagion, modeling engineering contagion, and then down the road, I'm going to talk about two strategies how to contain, how to mitigate contagion. One approach is I call it plenty of room at the top, meaning controlling the system from the perspective of the global architecture, and another strategy mitigate contagion by looking at the substructures within the system. So there are two approaches. And again, please, you can ask me any question at any point. Really. So the first thing I would like to do is sort of to set up the playground for the discussion and to mention a variety of things uh, that are relevant to complex systems, and those themes penetrate, every aspect of this field. And so the first one is universality. Many of those concepts, originate in physics, so the theory behind those names. But universality is the idea that the same patterns emerge across diverse systems, regardless of their microscope. So it's okay to take a look at the system from above and try to find patterns, regardless of all of the minute details that can determine the behavior of the system. So, for example, in the context of find in society, so you can model them as networks, and you have all of those networks share some common characteristics. So that's one example. The second theme is the idea of wild variability. Means that in nature, or in society, you find often distributions related to the things that you measure, that are fat relative to the normal distribution that we used to be exposed to in school. Uh, Essentially, the idea of distribution means that there is extreme inequality in event sizes or connections, meaning that you have few elements, perhaps, but it could be any other component, or any other size of thing that you measure. You have those few elements that dominate, while the majority remain small or sparse. Uh, this wild variability aspect penetrate, many aspects in society. Think about, a network. In a network, you have uneven distribution of connection, and because you have uneven distribution of connections, then you can exploit it. For example, here you can exploit it here. Oh, sorry, I tried to highlight. Hopefully you see my mouse when I move it. So you can exploit the idea that some nodes are highly connected, and you can manipulate them, or in order to diffuse information fast. That's one example of one consequence of wild variability. You can think about the idea that wild variability also creates or leads to the idea that you find what we call giant components in systems, meaning a component of interacting units, and the size of this component is giant. We call it giant, meaning it's so large, and it can be shown mathematically that wild variability implies the existence of these fully connected, or highly connected system that enable the spread of all kind of stuff. So if you take a look, for example, at events here on the right-hand side, events associated with civil unrest magnitude. So you find that the distribution, again, are also aligned with the fat tail distribution. And you find it in society, species distribution, income distribution, city population, word frequency, all of them, are associated with this characteristic of wild variability. Uh, the next theme is coupling and correlations. Uh, it means that in many complex systems, particularly as they approach their critical sort of behavior, the extent of coupling or connectivity in the system and the extent of correlation tends to rise up, and you can measure it. So it means that parts of the system co-vary across space and time, reflecting both structural and dynamical interdependencies. So for example, in this picture, you see on the picture on the right-hand side is a system where the extent of spatial correlation is small relative to the picture on the right left-hand side, where components far away start to communicate with each other. The next, oh, maybe I should actually press it because that's interesting. So this aspect of spatial temporal correlations dominates various fields. And for example, if you by the way, when I say correlation, it could be structural correlation within the system, but it could be correlation related to the behavior of different components. So different components behave. It could be that the underlying infrastructure is correlated. So for example, if you take an engineering system, uh, you find that the degree correlation within the system, meaning the idea that one component creates some patterns of interaction with other components that affect the way that contagion spreads along technology networks, for example. If you take the classical Ising model, as then you find that system that are below the critical temperature, like the one on the left, creates a correlation which is not fat-tailed, which is thin-tailed, essentially, like the red line that you see here, as opposed to system that are at the critical level, creates correlation that are long distance or long range. You find in civil unrest data that that as we approach uprising or approach high level of activity, the system starts to exhibit temporal memory, meaning that there is correlation across time, and events starts to relate to each other. Uh, if you take a look, for example, this picture, then you can start measure the correlation between stocks over time. And so this picture creates networks based on whether two stocks are correlated or not. And what you find is that for example, this picture measures, uh, in this picture, we measure the correlation of various networks. And as you approach a crisis, like the subprime mortgage crisis of 2008, then you start to see that the network becomes more densely connected due to those correlation between different. So you see it all over in many, many different systems. The next theme that is prevalent in many systems is that the topic of or the concept of phase transitions, meaning that in many systems, a phase transition is essentially a sudden shift in collective behavior as the system moves between different stages of organization, right? So, this picture on the right illustrate conceptually the idea. The x-axis are the external conditions, the environmental conditions. The y-axis is the system state, the thing that you measure. And you find that as you change those conditions, environmental conditions, for example, suddenly the system experiences a sudden shift in behavior. So this is something we want to study and to predict. Uh, so for example, just to illustrate my point, um, you find this is something very prevalent in physics. Uh, for example, in the icing model, as you change the temperature of the magnet, suddenly the average magnetization of the system uh, changes dramatically. So higher temperature meaning no magnetization, the system is disordered. As you reduce the temperature, suddenly the system starts to behave like a magnet. So that's something that you see in physical systems. You see it in other models like percolation and so forth. So we want to study this kind of phenomenon in social systems. So, for example, in when people collaborate with each other and try to solve an engineering problem-solving problem, then we found that as you increase the coupling in the system, meaning the degree by which activities are related to each other, suddenly the time that it takes to complete the project or the total budget that you spend or the extent of the spread of errors in the system rises up dramatically. So low coupling, all is good. High, suddenly you change it and there is dramatic changes in the market. Stock market also behaves similarly. Uh, in this case, the environmental conditions is the extent, the ratio between panics and fundamentals, right? So as you change as you create panic in the market relative to fundamentals, suddenly the systemic risk in the system rises up dramatically and the system collapses. So we want to study this phase transition in ecosystems. Well, let's say you increase the harvesting or the harvest rate, suddenly the biomass in the ecology is collapsing. So we want to study that. Another theme is what we call out of equilibrium dynamics, that complex systems are not in equilibrium. They're always in a stage of changing equilibrium, dynamic equilibrium that is changing adaptively. Uh, so essentially, it says that the system, the behavior of the system is shaped by internal influence within the network, as well as ongoing external disturbances coming from the environment. So, the classic example is the sand pile model, right? You had grain of sands from outside, and the system experiences from time to time, avalanches, and due to those internal forces between a variety of grains within the system. Financial crises also behave similarly. You have fundamentals, but you have also investors that are connected to each other and influence each other in some way. Uh, and you find it in civil unrest also. So here you see an example of the civil unrest in France, 2005. Everything started in some region, in some suburb of Paris, and and due to all kinds of frustration built in society, and those frustration at some point erupted, creating disturbances across the system until the system at some point relaxes, but then the cycle begins and so on. So you find this kind of out of equilibrium dynamics in many different systems. Any question, please ask me any question, because there is a lot to talk. I will not. I'm not going to probably finish everything, but please feel free to ask me any question. So what I would like to do now is simply present a way how to measure it, right? How do you measure it before we get into modeling? And so, um, just to, and I want to demonstrate. I know this slide sounds very strange because I'm going back 2 million years back in history, and we live the moment. But if you think about social, it is a fundamental a fundamental element in society. In my view, it is the element that changes, civilization as we experience that. So if you think about it, if you level of cultural and technological complexity over time, at some point 45,000 years back, during the late Stone Age, suddenly the level of cultural complexity and technological complexity rose dramatically, and one of the reason is that population density on Earth started to rise. People started to connect with each other. People started to learn how to behave, how to create all of the technologies that they create, and so forth. So, so social influence, population density, connectivity is fundamental to everything that we see. Uh, More down to earth examples. So if you think about fads and fashion trends, one example of these social epidemics, social influence, conventions, norms, and standards. The adoption of one norms relative to another is another example of social influence. If you think about ideas and innovation, how culture, religion, geographic field, areas is determined by spatial epidemics. Rumors also is another example of social financial bubbles, social unrest, and even obesity is an example of social influence. Uh, so, um, so in the Ising model, you already see, in the classical physics model, this is the fruit fly, uh, Ising, actually. Very interesting. He published one paper in his life, not his fault, but the most important paper, right? So sometimes it's good to write one important paper that changes everything. So if you take a look at the Ising model, uh, and you measure the magnetization of the system, right? So the Ising model says that magnets, try to align, but there is also an external influence of temperature impacts the behavior of individual magnets or spins. Uh, so if the temperature is very low, less than a certain number, which we call temperature, then the probability distribution of the magnetization is bimodal, meaning that the system is either up or down, right? Uh, if when you raise the temperature slightly and you come to a certain critical temperature, suddenly the distribution becomes pretty much flat, as you can see here. And if the temperature is really high, then the system is getting into a disordered random behavior, and then you find the normal distribution, right? So remember this picture because the model is a practical model how to work with, because it's very difficult to work with the Ising model analytically. So we developed a simple model that enabled us to measure a thermometer. So the question I'm asking is, what is the social influence identification problem? The question is observed behavior driven shared external factors, right? So you have a network and you have those, external influence impacting individuals within the system, but those individuals are also influenced by the neighbor in some way. And so the question is, how do you discern? How do you uh, entangle the behavior of individuals with respect to this external relative to internal influence within the network? How can we know data, right? The only thing we see is observational data. So, a very simple model is that think about a network uh, that where some of the behavior in the system in this case is binary. So People vote red or vote blue. Uh, and you have also in the system, you have also some nodes that are fixed, always fixed in their behavior. So, for example, you have, let's say, two nodes that are always voting blue and three nodes that always vote red. And people within the network are free to change their behavior. So you can think about these external influence as, ideology or some influencer or media and so on. Uh, and you have those free voters within the system that change their behavior, right? So the initial system is like that. And then at some point you choose a node randomly. This guy, the blue guy, right? The blue guy denoted here by black at this point. I chose this guy, and then I'm looking at the neighborhood of this guy. The neighborhood is the external influence and everything around that guy. Then I'm choosing a neighbor randomly. So I chose this neighbor here. All right, the neighbor is red. So then you copy the neighbor state. You become red, and eventually the final state is as follows. So essentially, you started as a red. All right, so yeah, that's what you get. So we want to model this kind of behavior. So it turns out that, by the way, this kind of system you can it's a very simple model, but you can apply it to various models. You can collect data from surveys, for example, regarding the preference of people to use transportation modes, different type of transportation modes. So bus relative to car, or pick one job over another, commit a crime or not, smoke or not, get an abortion or not, vote or not, trade the stock or not, do an MBA or not, right? Riot, protest or not, adopt or reject sustainable farming methods, right? To be or not to be, any one of those binary questions that you can ask. Now you might ask at this point, can you extend it to non-binary? Yes, you can, but it will take me to a different talk. It's very complicated to come to that. But at this point, we focus on binary choice. You find similar dynamics in nature. Like, for example, dolphins and they learn from each other. So the question is, use one hunting strategy over another, or activate chemical defense or not in the context of plant-to-plant signaling, or firing or not firing a neuron. Epilepsy, active inactive gene expression, for example. If you examine, for example, the fruit fly's embryonic genetic regulatory network. So again, you have this kind of activated gene or not, and external influence also impacting. All right, so you take this network and you analyze it. It turns out, after a lot of work, that you can derive this distribution of the number of nodes that vote a certain color, let's say blue. Okay, so it says that in steady state, when you run the system, then when the system reaches a certain equilibrium point, then the probability distribution that you will find a certain vote blue, let's say, is given by the expression on the right hand side. Now, in this expression, alpha and beta, remember, are those parameters that comes from the environment. Alpha are those external environments that lead you to vote blue, and beta is everything outside that propels you towards voting red. So everything is determined by alpha and beta. And so this system behaves in very interesting way, very similar to the Ising model, meaning that if you increase the external influence, if you make alpha and beta large numbers, and you increase the external influence, then the system is getting into a disordered type of behavior. So you get this type of distribution that you see here, the red line, alpha equal beta equal 10. That's a normal distribution. However, as you decrease the external influence, meaning as alpha and beta are decreasing, it means that each individual each individual is impacted by the neighbors more than the environment, then in this case, the system will get at some point to a phase transition. And the phase transition will happen when alpha equal beta equal 1. So the distribution becomes flat, completely flat. So it means everyone votes up and down completely according to a random walk. So that's the black line that you see. Now, if you keep decreasing alpha, this kind of bimodal behavior, the red line, the red function that you see here, meaning that the system is getting into an ordered state where everybody vote red, blue, depending where you start from, right? So there is a phase transition that is happening. It's now, well, you can do the logic here is the real numbers, right? So it's fraction rather than with the actual number. So instead of working with the actual number of voters in the system, X, meaning how many, you measure the fraction, denoted here by V. So you measure the fraction of nodes that voted a certain color in the system. So it turns out that you can the in the system that voted blue is simply the ratio between alpha and divided by alpha plus beta. And if you examine the variance of the system, the variance of this distribution, remember the variance of this distribution, you can decompose it into two parts. The first part is due to external influence, meaning if you turn off all of the internal connection and people listen only to the environment, then Bernoulli random variable, and you just listen to the environment. On the other end, there is a second component here, which is influence. So this variance can be decomposed. And what we want to measure is that's what we want to measure, the peer influence aspect in real systems. Okay, so maybe I'll skip that. If you're interested, I have a very interesting theorem about it. But anyway, so what is the philosophy here? The measurement philosophy. So you can use the same model to measure social influence based on temporal data or based on spatial data. So temporal meaning that you measure the network over time. So you measure the network at time 1, time 2, and so on, and then you measure how many nodes went up or down, and based on that we want to study social influence. On the other hand, in political science, one measures voting, for example, for president. Then in this case you have counties, and you each county, so you can actually measure. So this is spatial. You have various networks spread across space, and we would like to study social influence based on these spatial networks. So we have two philosophies here. All right, so let's see how it works. So the first thing I would like to show you is how to apply to financial contagion, right? So this is an example of a temporal kind of network of system. So you have the stock market at time 1, the stock market on day 2, the stock market on day 3. You can measure, you can do it at the second level, minute level, doesn't matter. You can measure it across time. You can simply up how many stocks go down during that time. So this is an example. Everything that I'm going to show you is an example of temporal correlations, phase transitions, out of equilibrium dynamics. You're going to see that. So I don't have time for jokes here, so I'll judge. Yeah, maybe that's just interesting. If you think about very interesting example, the South Sea bubble, 18th century classical case of bubble formation. So Isaac Newton, the great Isaac Newton, he decided to invest in the company, the South Sea, this company, and early on. At some point, he made money, and he exited very happy. Then he saw that his friend got, so he was very much influenced by his friend. So he re-entered the market with a lot of money. Actually, at some point, everything is based on real data. And at some point, the stock reached a certain, high peak level, and the stock collapsed completely. And Newton exit broke. Actually, he lost his money. And when asked about it, he said, "I can calculate the movement of the stars, but not the madness of men." Well, that's great. That's good. That's let's see how complex systems can teach us about this aspect. By the way, you find these bubbles, right, all over, right? The Wall Street crash, it's not new. Dot-com crash of 2000, of 2008, and so on and so on. So the idea here is that you have a network, right? And stocks can point up, can go up, can go down. And then those external influence are represented by the good news and bad news, right? That people are tuned to, or fundamentals. So remember, this is the distribution. Everybody remember, right? So this is the distribution of how many stocks pointed up during a certain in a certain day. Let's say you collect data over time. So how many stocks pointed up? How many stocks pointed down? In this case, how many stocks pointed up? Right. So alpha is this parameter that measures good news. N is the number of stocks that you collect, and beta is the bad news, right? In this system. Okay. So you measure data, right? You measure daily behavior of the stock market. And remember the picture I presented before. There is a phase transition predicted at alpha equal beta equal 1, right? This is the point where stocks starts to behave like random walk before getting this model split in phase transition, right? So things start with a disordered behavior, like this normal distribution, meaning good news and bad news dominates the behavior. And as you decrease alpha and beta, you get into this economic crisis phase transition, predicted, right? Or critical point. And beyond that, the system is getting into crazy behavior where stock starts to go up uh, or down in very erratic fashion. So here you see measurement of the stock market, and you measure the core movement of stocks. Stocks went up and how many stocks went down. So here you have measurement of those parameters over time based on real data. So you start in 2000, right? It's like normal distribution. Everything looks beautiful. We are all happy, right? You see the dotted line is the real data. Sorry, is the dotted line is the it is uh, the solid. Apologies. Solid is the real data. Dotted is the model, right? The distribution I showed you. So this is based on daily behavior of the market. So as you can see, you start with alpha beta. It goes down to in 2001, go further down and so on. And in 2008, you get this flat behavior that I mentioned before, right? This flat, this critical point that you often see in many different systems, this economic crisis transition that is happening. This diagram may be illustrated better. On the y-axis, you measure this alpha. We assume that alpha equal beta because the system is pretty much symmetric in terms of the distribution. So we have only one parameter rather than estimating two. And what you see indeed is that alpha is declining quite systematically as you approach the financial crisis, and it hits the level alpha 1, right? Remember this predicted number very much near the financial crisis here, right? So that leads to one idea that I wanted to mention. Flattening of the stock market distribution or any other distribution may serve as a measure of vulnerability in the system, right? So that's one example. Any question? There's so much to talk, so you have to stop me. Yeah. Um, So another example is political science, right? So in this case, you examine voting behavior in presidential elections. So this is an example of spatial correlation, phase transition, out of equilibrium dynamics, everything that we tested. So in this case, you have a network. As before, people vote in different ways. But an alpha and beta in this case simply represents those external consistent partisan bias that everyone in society is influenced by, right? Prejudice, attitudes, orientations, party identification, upbringing, religion, ideology, anything that influence a person. And the peer influence is within the network, is everything around you, the friends, the neighbors, the family, and so on. So this behavior. So, so in this case, the data is across almost 90 years of voting at the level of each state, at the level of each county. So you have information at the level, really, at a minute level. And again, what you do here is that each county is a network. Each county is a small network in itself, right? And we assume something just for the sake of analysis here, that alpha and beta are common to a state. You might change it. You might say alpha and beta is common to a county, right? Each county has different alpha and beta, but we assume that alpha and beta is unique to a state, right? In this case, Texas, uh, right? So you have this right this network, and doesn't matter how the procedure, the estimation process, very complicated. How to estimate alpha and beta conceptually think about it, that each county is a network, right? Is a network, is a small network, and we can estimate those parameters based on voting data at the level of each county, right? There is a way of doing that. Um, Taking into account the number of people in the county and other related public known data. So the model is verified in many ways, meaning we predict a certain distribution of voting behavior across counties, and indeed we find that the distribution predicted by the theory. I will skip that. Uh, One interesting aspect that you can learn from it, there are many ways, but if you take each state, if you take sorry if you examine a particular election year, and you measure the social influence for each state, so you have a vector of all states in a particular election year, and then you can start to correlate different vectors with each other, uh, to see how different election years are related to each other. All right. So this is what you see here, is a sort of a clustering of the correlation between different election years. And quite interestingly, you can replicate historical events. Uh, you see the yellow color and the white, meaning high level of correlation. So the clustering analysis shows you is replicated. I mean, you can explain history, right? The first one, second one is the Wall Street crash. The next one is what we call the realignment of the fifth party system. Then you have transition. This is the post New Deal era, the Watergate scandal, and so on. And finally, we are currently in the sixth party system. And you find indeed that you can sort of social influence can explain different events, historical events actually happening. Uh, you can also measure time, and you find that there is a way to normalize it, but the basic idea is that social influence was not dominating for quite long time until around the 90s, 1996 and so on. It started to rise dramatically, right? So this is the graph that you see, you measure. sort of a phase transition, right? That is happening very, social influence and sudden transition that is happening. We can talk for an hour why, there is an explanation why it happens in the early 90s and so on. But that's something you can do with this kind of analysis. Um, you can also measure social influence changes over time, right? So just to give you an example, the geography of social influence. So it shows you pockets of social influence. So black meaning influence. All right. If you see white, it means low level of social influence. And you see over history how the map is changing. This 1960, 1964, and so on, right? You have in the Northeast, you had this high social influence initially. It changes over time. Different pockets are created. At some point, we get to the current currency, map, and so on. So I don't have data about Trump, so I don't know about Trump. That's a different story. Anyway, so that's the kind of stuff you can do with that, right? Try to measure social influence across time and see what happens. The Kim, how much time do I have? So I don't want to take too much time.
At least another 20 minutes or so, if everyone's on board to
Okay, so
continue on.
I'll try also to allow question and also address the question that people ask me prior to the talk. I will address them. Some of them will be addressed now. So, the next issue is really how do you measure it, right? Sorry, how do you model it? How do you model social contagion? So social influence is simply an element that mediates society, right? You can't have contagion without social influence. So one example, a case that we examine is the civil unrest, right? That is the current Trump. So civil unrest. So here you have, all of the ingredients of complex system beautifully. Temporal volatility, what we call burstiness, scale invariance, spatial contagion, out of equilibrium, phase transition, and spatial temporal correlation that I'm going to show you. So the model is very simple. You can think about, and you can model disease spreading or any other social phenomena using this kind of modeling. But the issue is that you can divide the country into regions, and each region is susceptible for unrest or discontent behavior. And first of all, you create a network that is embedded on top of the country. And this network simply represents media links, social links, and so on. So you have a grid and you impose some network on top of the grid. So each region can become susceptible to unrest behavior. And at some point, those regions burst, and there is a spontaneous outburst of protest or riots, and those protests spread across social links, media links to other region, right? And so everything is controlled by probabilities, right? You have unrest, susceptibility probability, spontaneous outburst probability, infectiousness probability, and so on. Probabilities. And, this system exhibit very interesting behavior. For example, here you see versus time. So we find that unrest goes up to a peak and goes down of unrest behavior, right? Another thing, you can measure the autocorrelation. You measure the unrest activity over time, And the high level of unrest behavior, you have a very unique autocorrelation spectrum that is created. That's a predictive model in the sense that there is a very unique picture of the autocorrelation related to the stream of data, stream of unrest behavior over time. Uh, so this autocorrelation is simply there is a lag that you can change, and you can measure the correlation for different lags, right, based on time series of data. So there is a very unique signature related to moments where unrest starts to rise. Unrest size distribution is 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 long tail, as we mentioned before, this concept fat tail, right? And particularly, it becomes fat tail as you approach the peak of this distribute the peak of the um, uh, unrest susceptibility also tends to go up and down, meaning regions become susceptible over time, and when they cross a certain threshold, that's the time where things bad starts to happen, right? And again, you can measure all of those thresholds based on surveys, based on Twitter data, based on all kind of stuff. And, we don't want to share everything. Yeah, you can measure all kind of thresholds, right? That can happen. But the issue is that as unrest susceptibility start to rise, as you cross, as you cross those certain threshold, that's the time where the autocorrelation starts to create a certain signature, and bad things happen. So how do you testify it? How do you test it? There are all kinds of ways to test it, but so here you see real distribution generated by this kind of model relative to real data in different continents. So you find very beautiful fit to the distribution. Uh, uh, it's interesting to take a look at the effect of media and social hubs on social unrest contagion. Meaning, my point is that you can measure the impact of the network architecture connectivity of the network connectivity on the extent of unrest behavior. And so it turns out that as you create region which are highly connected, and then you start to spread the social unrest starts to spread rapidly from one region to another. So the analysis convey this story that media and social hubs amplify civil unrest contagion, and it can be used if you want to propel a revolution, or if you want to contain it. If you're a government, you can use it for positive or negative aspects here. Um, Regarding the phases, remember I mentioned the phases that you see here. So let me just go back here. Sorry. Oops, sorry. I'm stuck here. Okay. It's quite. Oops, restart the program. Okay, hopefully not. So I mentioned the phases, right? If you take a look at this diagram here, unrest size versus time, you see that you have these phases of unrest, right? It goes up, goes down. So essentially, there is a bubble, and the bubble burst, and so on. And it turns out that this is true. This kind of phases happening in real data, and so this is the kind of model that we see here. So indeed, you find phases in real data, and so test it. We don't have time for that, but there is a way how to test this kind of phases of unrest behavior, right? This kind of idea fits the data very nicely. This kind, the concept that you have phases of phase transition um, fits very nicely into data. All right. So that's the idea. Um, okay. So again, civil unrest is spatially autocorrelated, right? And as I mentioned, there is a signature that that you can measure, meaning different region. As you approach the peak of unrest behavior, be correlated with each other. Uh, unrest behavior in one region, right? So one can measure this kind of correlation, spatial correlation. Uh, this map shows you measures civil contagion on Earth, right? So you see different countries. Uh, so the darker the color, meaning the more it is. So you find indeed that countries that exhibit high level of contagion, civil unrest contagion, tends to be clustered next to each other. I think that it was interesting. Modeling engineering contagion. Wow, that's a different story here. So here, when we say engineering contagion or technological contagion, the infrastructure as well as of creating those engineering systems. So in critical infrastructure systems, like the spread of substation failures. It shows you the recent map from the events in Europe, in Portugal and Spain, actually, right? The recent outages out in Spain and Portugal uh, and this is the power grid of the US. You have also contagion in communication systems. Uh, or if you think about collaborative problem solving, engineering problem solving, contagion in engineering problem solving, right? So the tendency of open problems to be created over time within the development. So you can model it using very similar models of contagion. Uh, so you can think about a model cascading failures or open problems that spread like a disease across the system, right? About infrastructure systems, you can talk about substations, for example, highest level of capacity, and when they reach the highest level of capacity, the the uh, the load tends to spread to neighboring substations, and when they reach the peak level of capacity, spread furthermore, and then you have failure within the entire system. Or if you think about a group of individuals trying to solve a large-scale engineering problem, then you have epidemic contagion of open problems, right? So something that looks like that. Red is open problem, blue is closed problem, and you have open problem till you solve the problem. Uh, so you're able to actually model this kind of systems. And then the question is, how do you control it, right? And what do we learn from it? So I think a very important aspect from all of these analyses is that network fluctuations and correlations within the network, plus coupling and influence between different elements within the engineering system, leads to engineering contagion. Topology, and you need influence between different elements within the system. And so there is a phase transition. Uh, if you start to increase the coupling and the influence between different elements within the engineering system, then there is a very rapid switch between a stable and unstable system, right? As you increase the social influence between different elements. Uh, and this transition is controlled by the extent of correlation within the network, that exists within the network. And there is a very a very subtle mathematics below it. Really, what determines what are the amplifiers within networks, and if you want, I can explain that, but there is really analyze it at a very precise level. All right, just two ideas, and then we'll wrap the basic concepts here. Approach of controlling engineering contagion is by controlling the architecture top down, meaning here on the left hand side is the behavior on real engineering system. So if you if you degrade the highly connected nodes within the engineering system, then the system will exhibit a rapid contagion. All right, so those diagram here above, right? So if you increase the fraction of degraded nodes within the system and you focus on the hubs, rapid contagion. On the other hand, if you do it randomly, then systems are very, very much robust. Engineering systems are highly robust. Now, you can also immunize the system, right? You can use it to improve the system. So if you enhanced a particular nodes within the, meaning you make them less impacted or influenced by their neighbors, right? So if you focus on the hubs, then contagion is suppressed. On the other hand, if you have a budget and you try to improve, a node randomly within the system, then you don't achieve much suppression within the system. So it tells you simply on the bottleneck. Focus on the bottleneck, right? Identify the bottleneck and focus on the bottleneck. So strengthening or weakening a few critical nodes can control the spread of failure within the system, right? That's the idea. And finally, another approach, which I call there is plenty room at the bottom, meaning we can actually improve the system by focusing not on the hubs, but we should focus on the substructures within the system, the subgraphs, the small subgraphs within the system, right? The small groups within the system, the small connectivities within the system. For example, what you see here is different subgraphs that include 3 nodes, and I measure which one of them suppress. So this graph is better. Pattern of connectivity better suppresses contagion relative to this graph, right? So you can measure it simply. This kind of phase diagram shows you which substructure controls better, suppress better contagion within systems. So you may say, well, amazingly, it turns out that the subgraphs that highly suppress contagion appear in real system. So that's what you see here in those two pictures. It turns out is abundant in real systems, real engineering systems. So here, for example, this column shows you the subgraphs that suppress contagion the most based on simulation. And what you see here on the right-hand side is the ranking of those subgraphs in real systems. Vehicle design with hundreds, for example, vehicle design with hundreds of activities, or all of those networks includes hundreds. You see that what we predict to be subgraphs that suppress contagion indeed appear in real system at the same level of ranking. This diagram is even more surprising because it shows you see at the bottom, you see the different subgraphs, and is a sort of a profile that shows you the abundance of those subgraphs in real engineering systems. And what you see is that the profile is the same across completely different systems, right? If you see the box going up, it means it is prevalent within the system. If you see the box here going down, it means it is suppressed relative to a random net. This kind of suppression uh, and prevalence within the system is very much similar across systems. So that leads to the final idea that we can control uh, contagion within the system by evolving resilient network through motif selection. So we need to evolve the system actually to behave to include all of those uh, that promote less contagion. So essentially, my point is that you start with some variation, right? Those are engineering networks that exhibit a diversity of subgraphs, actually confer greater resilience. Then you select, right? So there is selective pressure that will favor those subgraphs that suppress contagion, and which is transmitted through mimicry, copying, learning, engineering best practice, and so on. And eventually, over time, you will end up with systems that are enriched with those resilient subgraphs within the system. So that provides a different way how to control the system from the bottom up rather than top bottom. So those are some of the ideas, and I'd be very happy to open to questions. Um, there are some questions that people ask, and I'll be happy to address additional question. Uh, yes, please, Robert. You can.
Yeah, so how do we influence our society to favor the interests of the 99% instead of the 1%?
Yeah. So if you go, the question is what are the level influence society, right? That's if you go back to this diagram, it shows you. It provided a sort of sorry. If one way of doing that is to create to connect different parts of society. About connectivity by connecting different parts of society, different segments of society, uh, by creating social things, connecting. You will spread the message, right? The message that you're interested in. Sort of grassroots movement to create those connected regions, connected individuals that over time will lead to a change, right? So it's a process. It's not in one day. It takes time to grow those networks. So, Lior, please.
Yeah, so my question is, I'm interested in identifying the tipping points where the behavior changes, right? In
Yeah,
financial trading, where you go from normal volatility to high
yeah.
volatility, or the tipping point where you say there's enough momentum for investing in renewable energy. And so if you can talk more about your experience about how accurate or timely those are identified in the system that you
Yeah.
investigated.
Question. So, when we did the analysis of the financial, uh, so first of all, we have to admit that the prediction is not immediate. Is not immediate. There is where I don't show the entire graphs, but there is some signature, right? As you measure this mimicry parameter, right? Like the way we do it here. You can measure this parameter over time, and when it gets below a certain number, it means that something bad is going to happen. But the problem is indeed that the window of prediction is not immediate. For example, in financial system, there is it takes a couple of months before. So I cannot make immediate money from that, but at least you know that something bad is going to happen. If you examine a social system, so I presented the signatures, right? I mean, I didn't show you all of the data, but some of those, the strongest one actually that I found is to measure the where is it? Here, the to measure the autocorrelation within the time series data. So you collect as you approach here. That's what you see, the autocorrelation spectrum. As you approach, the autocorrelation spectrum starts to behave in a very unique way. Yeah, it's like it starts to create a pattern that you cannot. It's very unique, right? And it's not similar. So when I say autocorrelation spectrum, I mean there is a window, sliding window, where you measure the correlation within the time series as you move the sliding window over time. So this is a very good predictive signal, for example. Variance also tends to increase. The variance, the volatility, you see what I call it volatility. The volatility within the system, again, based on a sliding window, starts to rise quite dramatically as you approach the tipping point. So that's another signal. The autocorrelation, mimicry, all of those parameters. And also, as you cross a variety of threshold that you can measure based on surveys, public data, actually. You can measure, it turns out, of the public as a predictor for the event to come. So you can measure the perception of the public based on different data sets. And that will give you another many threshold that tells you that something bad is going to happen. So you have different ways how to do it. And again, the best way is not to do it by single measure thing, right? And plug it into your model. Yeah. Antonio, sorry, please.
Hello, thank you so much for the interesting presentation. I have a question about the latest slides on motives.
Yeah.
I noticed
Okay.
the motive, yes, the triangle.
Yeah.
Yes, I noticed this one.
Yeah.
I noticed that the coupling influence is determined also by the length, the average part length or the shortest part length of the motives. If you have a motive with a very short part length, like A, or B has, I suppose, a part length of 2, C has a part length of 3, and maybe D has a part length of, it's more, there is more ways to go from one node to the other.
I absolutely agree. I
Okay.
absolutely agree. Yeah, I agree. It's the number of possible trajectories that can spread the contagion. Yeah.
Okay.
I absolutely agree. Yeah, in this case, it's simply, what the picture that you see here in a way capture your idea because the model takes into account, right, these possible trajectories.
Okay, so we may say that the influence has very much to do with connectedness, I suppose. If nodes are more connected, they influence more each other.
Yeah, but in
not-
this case, it's a directed network. So you have to consider the patterns of in degree and
Yes.
out degree. It's not an undirected network. But I agree with you. If it's an undirected, yes, the more links you have, the more problem you have. But
More
if
clustering coefficient.
if it's directed, then it's more subtle. It's more subtle. It's the pattern of connectivity, which is more subtle.
Okay.
Yeah.
And I have just another question. It's what kind of network?
Hey, Antonio, sorry to interrupt, if you take a look here at the bottom, you see at the bottom here?
Yeah. Yeah.
You see that one of them, this one, number
10.
10, is more
Yeah.
as more links in and out links, but it is more enhanced in real network relative to number 9.
Okay.
So it's not how many in and out you count. It's really the way that you connect.
Yes, of course, because the motives are different from each other.
Yeah.
Obviously, yeah. Could you tell just for I have a doubt about the model you presented at first. What kind of network did you use to follow that model? The first model with that formula with the ratio between the.
This one, yeah, with the financial, you mean the
No, the first one, the first formula you presented.
With the
Yes.
probability related to the
Yes,
probability.
it is a random network or a power law
Oh,
network.
it's a very good point. It's either it's a random network essentially, but the
Okay.
derivation was based on a fully connected network.
Okay.
Yes, but the same equation, it turns out, is very a random network. Yeah.
And does it apply also to power law networks, the same equation?
No, I don't know how to do it for a scale
Power law.
for other topologies.
Okay.
I mean, I don't know. I know how to simulate. I don't know how to
Yeah.
solve it analytically.
Of course. Okay.
I hopefully
Okay.
I try.
It's more complicated to model.
Very
yes.
different. But
Thank
you
you
see
so
the
much.
point.
Yeah.
The point here is that if you want to measure something, you don't need to be so precise. It turns out that you have to present a simple model that simply gives you the big picture of the influence, right? Yeah.
Okay.
That's the idea here. It's a good model to measure influence. A
Okay. Just a
sufficiently good model.
random connections.
Random connections. Yeah.
Okay. Thank you so much.
Absolutely. Yeah. So any more question I'd love to address? All right. So I think we're all set. Yeah. Unless. Oh, we have Clayton. Please, Clayton. Go ahead.
Yeah. Thanks for an interesting talk. So thinking about the design of an organization with respect to contagion, if I understand it, the contagion framework is neutral as to what is being spread or shared or whatever.
Exactly.
So an organization that's resistant to the propagation of bad ideas is also resistant to the propagation of good ideas. Is this right?
That's absolutely right. That's the dual sword, right, of society. Then that's a problem. That's duality within our society. That you have good stuff that we want to propagate. At the same time, we suffer the consequences of contagion. So I'll give you an example. If you examine critical infrastructure or communication systems, over time they were designed to be efficient, right? Everything was designed to make those systems efficient. And efficiency means that you create networks that are susceptible to collapse. Mm-hmm. And that's a problem in our society, that we want to introduce efficiency. And while doing that, we also make the system highly vulnerable to. Correct.
Yeah. Thank you.
Yeah. We need to be less efficient sometimes. Less efficiency is better as far as vulnerability is concerned. Well, thank you. Any more question left to address? There were a couple of questions that people ask on. I
think more efficient is better. This is Chris Cole, but I think more efficient is better, but you have to be clear about where the bottom is so that your efficiency doesn't overtake your resilience.
That's correct. That's correct. But the issue is that we don't control as a society, the way that we build our systems. It is in many ways, and there are forces beyond our control. And at the local level, people want to be efficient, right? Think about financial systems. You want to minimize financial risk. Then you create all of those portfolios, right? Or you start to trade to create many links with other institutions because you want to protect yourself. You want to make yourself efficient. But at the system level, you create instability. My point is that you are right, but it's very difficult to control what other people. It's a self-organized society, and people try to improve themselves and to become efficient on a local level. And when they do it, the system become overall efficient, but then collapses.
That, that actually is my earlier point that I was asking. How do you quantify the kind of social aspect? Because to me, how a person or how even a group of people interpret influences will shift from person to person, from group of persons to group of persons.
Yeah.
And so
Yeah.
it just becomes that to me is more volatile.
Yes. So I think what you refer to is how do you relate different networks, right? Right? If that's my understanding of the question.
That's a good way of rephrasing. How do you
Right.
different networks?
Right. So you can use the same uh, the same methodology because in this case you have multi-layer networks, right? It's not a single network. You have think about the power grid, right? The power grid is controlling the internet, right? Communication networks or transportation networks. That's what happened in Europe last week, right? So one network, right? So in society, think about educating people how to use COVID vaccine, right? You can target certain nodes within the social network, right? The hubs, for example, and to spread the behavior from there within the network. So in idea, you can use the same concept that for spreading information within a network, even if you deal with multi-layer network. It's the same idea. Using hubs, using more links, and so on. I don't see much difference when you deal with multi-layer network. It's from my perspective, it is a network with different characteristics. Right? But at the end of the day, you can one network impacts another within the same framework. Robert, please.
Okay, thank you.
Yeah. So, do you see that there's some kind of phase transition going on since Trump came in this time? And where do you think that's going to end up?
Good point. First of all, I don't have data. So, I always try to build models only if I have data. But, I do is really to rewire the networks within the society, right? He wants to completely, break down different institutions and does rewiring the different activities within society. So I don't know where it would lead, right? What kind of rewiring or what kind of new patterns will emerge from this kind of strategy? But I do understand the strategy. The strategy is to sort of eliminate certain links within the system, rewiring them, and see what happens. Right? That's what he's trying to do. I predict. I don't know. I can't predict where it would be.
It sounds like the premise is to decouple things because we have too many couplings.
Yeah.
And reduce the amount of couplings. But I think you're going to run into the same problem, which is the social factor. It's going to produce unpredictable results.
I totally
because we
yeah,
have
that's
so
the
much
idea
momentum.
of the rewiring idea. A completely dismantling institution is really, and so that's a strategy. It's a political strategy, and could work for him, depending where it would lead, right? What kind of network would be created after you destroy it?
Yeah, I think you have a lot of momentum for the old strategy. You have generations of momentum for the old network strategy. And even though you have removed the coupling for the current strategy, the momentum, I think, will start to generate additional communication between existing networks, and they will be, how do you say, less certain, but they still exist. And over time, long time, before the new network actually functions as architected.
Exactly. So yeah, that's an interesting question. You know, what happened in society when you dismantle some of its structure, right? Architecture, and what kind of architecture would arise in the future? That's a very interesting research question. And can you predict the kind of rewiring that will happen? I don't know. It's a good question. I don't have an answer.
Thank you, Professor Braha.
Thank you.
For an
Thank you very
amazing
much, everybody.
presentation.